A parameter on a graph is a number related to a graph. Now, we already have two of these that we've used repeatedly: order, size. What's the order of a graph? Number of vertices. Size? Number of edges. Great. These really problematically only describe the gross structure of the whole graph. They don't really give me very much in the way of fine detail. So I'd like to start expanding my collection of parameters. So let's talk about things that are parameters to specific vertices. The degree of a vertex, usually written DEG of V. Sometimes if I want to be specific about what graph I'm in, say I have more than one graph involved, I'll put it as a subscript, is the number of edges incident on V. Or an equivalent way to say it is it's the number of adjacent vertices. However, that definition really only applies if we're looking at a simple graph. Why won't that definition apply to a multigraph? Aha! So I could have one neighbor vertex, but it could have multiple edges that connect it. And that would change the distance, the number of edges would be different than the number of vertices that are adjacent. So if I'm in a simple graph, these two definitions are equivalent. If I'm in a multigraph, it doesn't cut it. We're going to work with edges rather than vertices. Same thing is true if I'm in a pseudograph, because then I could have a loop, right? A loop would make a vertex incident adjacent to itself. But then that edge actually touches that vertex twice. Once on the way out, once on the way back in. Crap. So that would definitely change the relationship going on here. Most of the time, we'll count it by number of edges. In a simple graph, the size of the neighborhood is equal to the degree of the vertex. Again, that's because these two definitions are the same. But the set N of V, the neighborhood, is the set of adjacent vertices. If I want these two to match, I have to be in a simple graph. Questions? Very Mr. Rogers of us. Here's your neighborhood. I don't care whether it's a beautiful day or a crappy day. Here's your neighborhood. All right. What does it mean for the degree of a vertex to be 0? No edges. I'm all alone. Such a vertex is called an isolated vertex. On the other hand, what if my degree is 1? What's a picture look like where the degree of a vertex is just 1? Well, then both would have degree 1, right? But I could have one vertex of degree 1 in a larger graph, right? But that means it's just stuck out on the edge all on its own, right? Here you are, the end of the branch. All of that, that's it. This is your only lifeline. We'll call it a leaf on a branch. Although maybe that descriptor should be reserved for certain kinds of graphs, so we'll sometimes call them end vertices because they're the end of the road. If every vertex in my graph can be assigned some degree, that's going to be a set of integers, right? Smallest one possible is 0. The largest one depends on my graph, yes? But there will definitely be a maximum possible degree. Why? At the very worst, I know my graph has a finite number of vertices in it. If something is connected to everything else, that's as big as we can get. This set contains its supremum and infimum, all you 207 people. It's got a maximum and a minimum. We will call little delta of G the minimum degree. Well, if little delta is my minimum, then I'm going to make capital delta my maximum. What do you know about those two numbers? Every vertex in your graph. What do you know about those two numbers? Great. What else do I know about them other than they're integers? But you're absolutely right, they have to be integers. Can't have half a vertex. It would be weird. No, because those are integers and V of G is the set of vertices, right? So they can't be in the set of vertices. Vertices are nodes, they're dots, objects. Jonah? What about depending on the amount of vertices?
So max would be 10.
So let's assign that. Suppose G has order n. We've got n vertices. What do I know about those two numbers? In a simple graph, I'll give you from 0 to, but why n? If every vertex in the graph is connected to this vertex, I can't be connected to myself. Because I'm in a simple graph, no loops, at the n minus 1. So I have for every vertex v. Here's a graph. Page 32, figure 2.1. But here's a graph. Next to each vertex's label, write its degree. Nice bright color will work from left to right. Degree of x. Degree of y. Degree of z. Degree of w. Degree of v. Degree of u. Delta of g, lowercase. Zero, smallest of those numbers. Capital delta of g. Two questions. What's the total of all the degrees added together? How many edges on this graph? Plane. The number of edges is half the total degrees. Or the total of all the degrees is exactly double the number of edges. This is in our textbook called the first theorem of graph theory. That's actually not the way I was taught to call it. I was taught to call it something different based on the way we prove it. The proof of this is one sentence long. Y is the sum of the degrees exactly twice the number of edges. Every edge connects two vertices. So when you count an edge, when you count the degree, you count that edge twice, don't you? Once from each end. It's the handshake. I didn't. Simple graph, right? But even if I counted a loop, the loop goes from here to here, then it would have to count in the degree twice. That edge hits that vertex twice, so one edge. I'm shaking hands with myself, don't I? Order. The order changes the size, right? I'm confused about what you're asking me, Ben. The number of vertices is the order. The size is the number of edges. So that's my size, M. If I have a loop, that's another edge from the vertex to itself. I should count that vertex as it goes. Sorry, I should count that edge as it goes out and as it comes back in, right? Because it touches the vertex in two places. Stuck a hand out to start the edge. I took that hand to finish the edge. I'm shaking hands with myself. There's my loop. But if I shake hands with you, we count that edge once for you and once for me. So technically, Ben, a loop is incident on a vertex twice. Does that help?
Yeah.
It comes out of the vertex and it goes back into the vertex. As a matter of fact, one of the things I was taught to count the degree is to draw a little circle around each vertex. Count how many times you cross that circle. So if I go back up to our graph and I draw a circle around any of these vertices, a small circle only containing that one vertex, then I'll hit each edge as I go around it, right? So we said this had degree 4. 1, 2, 3, 4. There we go. If I went around the vertex, I'd hit the loop on the way out and the way back in. Questions? Oh, look, it's a psycho word problem in graph theory terms that I hate to tell you this, could have been asked in Algebra 117. You could have been asked this problem in 8th grade if you knew what these words meant back then. I claim, yes, you can find the number of vertices in degree 3 and degree 5. I would like you to find that. How though am I supposed to do that? Hang on. I'm abbreviating quickly to keep up with you. Degree 3 VTCS, vertices. Y is degree 4 vertices, Z is degree 5. Now, what was your first equation there? Well, that makes my life easier, doesn't it? So, well, there you go. X plus Z equals 8. I'm already down one variable. I like that.
I'm going to say 3x plus 4y plus 5z equals 27. We can eliminate that null term.
I don't think this is right.
That would be
Because I got to multiply by 2, right? The number of edges gets multiplied by 2. That's our handshake result. Because each vertex of degree 3 contributes 3 to that count. Each one of degree 4 contributes 4 to that count. Each of 5 contributes 5 to that count. I should end up with 54 total. So this is theorem 2.1. So now I have two equations, right? Wait, how can I make this one nicer? I know y equals 6. 3x plus 4 times 6 plus 5z equals 54. That means 3x plus 5z. 4 times 6 is 24, subtracted over is 30. Two equations in two variables. You have your choice as to how to solve a system of two equations in two variables. You can use the method of elimination by addition, substitution, matrices, however you want to do it. You could graph the two lines and find their intersection on your graphing calculator. I don't care. Z is 8 minus x, put that in here. 3x plus 5, parentheses 8 minus x equals 30. 3x plus 40 minus 5x equals 30. So I get negative 2x equals negative 10. X equals 5. Z equals 3. So I have 5 degree 3 vertices and 3 degree 5 vertices. Lovely symmetry, completely by chance. Please note, there's only one possible way to draw this, right? If I wanted a graph that had those two properties, sorry, those three properties. Here are the number of edges, here are the number of vertices, here are the number of degree 4s, all the others are 3 and 5. There's only one of those. This is unique. I didn't have to draw it to try and find it. I don't want to draw it. It looks really complicated. I'm not going to deal with it. I don't have to. Questions? What if my graph is bipartite? And for the moment, if it's bipartite, that means the vertices can be divided into those partite sets, U and W. So I have the U vertices on the left and the W vertices on the right. What does my handshake principle tell me about the degrees of those vertices? Vertices U1 through US as opposed to W1 through WT. What do you got for me, Reese?
It should be the same.
But I don't even know that they're the same number in each side. What should be the same?
Degrees of each. You have M amount of edges, and you know the degree that's going to be 2M, and split into two parts.
Say that again?
If the edges is M, and we know that the degree of, like, the graph in general is going to be 2M, and it's 5 parts, that means it will be split into 2 parts, and the degree of both should be equal.
Degree, the total degree, not the degree of each vertex on each side, right? But the total. Aha. So why does that have to be M? I agree with you. That sentence is correct. But help me understand why.
I mean, bipartite means it can split into 2 equal parts.
Well, it can split into 2 parts, but why do I know they're equal and why do they have to be equal to N?
Because whenever you split those parts, you touch them.
Every handshake has to go across from one set to the other. So if there are a total of M edges and they have to go across, and everyone that comes out of U has to finish in one that goes into W, and vice versa. So they absolutely have to split M coming out of this side and M coming out of this side. They have to match up that way. We're going to say that a vertex is odd if its degree is odd, and a vertex is even if its degree is even. So, my problem with calling the previous one the handshake result is that this result is actually known as the handshake theorem. So much as I like to call the other one the handshake principle, this is the handshake theorem. Every graph has an even number of odd vertices? Why? I've written this as a corollary, which means it must follow from the theorem we just proved. The theorem we just proved said what? One sentence proof, people.
He has a G, so I'm in total degrees, you know.
So the total of all my degrees must be an even number. I'm going to create a new bipartite behavior here. Well, I don't even know if it's bipartite. I'm going to partition my vertices. I'm going to partition my vertices. I'm going to take the two vertices and I'm going to make piles. I'll pile all the odd vertices into pile 1. I'll pile all the even vertices in pile 2. Our theorem says the total of all the degrees must be even. How do I prove from here that this set has an even number of things in it? I'm going to count degrees. That's all I'm going to count. Let's look at this sum here on the left. It's really two sums, right? It's the sum of all the vertices in V1 and the sum of all the vertices in V2. I am 100% sure this number on the right is even. What do I know about this number that I've indicated here? All of those vertices are even, which means that that sum is a sum of even numbers. That sum must be even. If I subtract that to the other side, then that would tell me what about this number? Right, because this thing over here on the right is now even. It's an even number minus another even number. That thing on the right is even. How do you get a sum of odd numbers to be even? You have to have an even number of odds, don't you? Because each odd number is 2 something plus 1, you have to have an even number of plus 1s. The set of odd vertices contains an even number of vertices. Questions? This fact will allow me to kind of construct allowable sets of numbers for degrees, right? If I look at a list of numbers and I see 3 odd numbers, can you have a graph that works like that? If I know all the degrees but 1, I can tell you right away whether it's odd or even, just by counting the others. If I have a graph of order n, and the maximum of the degrees is n minus 1, what do I know about that graph? In terms of the adjectives we've already used to describe our graphs over the past 2 weeks. I'm not 100% sure it would be complete if one vertex, because remember, that's that maximum possible degree. There's at least one vertex that has degree n minus 1. If all of them have degree n minus 1, then it's complete. But what if just one of them has degree n minus 1? Or a couple of them? What other adjective could I use? Actually, I can guarantee you that's not true. Because a cycle is a loop, right? So here's a cycle of 4. What's a cycle of 4 look like? Maximum degree, there's 2. N minus 1 would be 3. I gave you an example of a bipartite graph we called a star. That's what Abigail said. Complete is where everything touches everything else, right? Here, delta of G is 3, right? I have 2 degree 3s. I have 2 degree 2s, but I have 2 degree 3s. So that satisfies this, and that's not complete. Getting warmer. Not hot yet, but I'm getting warmer. Oh, not empty just means I have an edge, right? And I have to have an edge to have a degree. So I'm happy with that. Gotta be connected. Because if one vertex is connected to every other, then I can go through that vertex to get anywhere, can't I? As a matter of fact, the distance between any 2 vertices is no more than 2. By the way, that's not necessary, right? A path of any length has maximum degree 2, and it's connected. So that's not enough to guarantee. That's sufficient, but it's not required. But what if I looked at vertices that weren't adjacent? What if instead of just looking at one vertex and 1 degree, what if I looked at 2 vertices that were not adjacent and I asked about their degrees? How do I prove a graph is connected? That would be a very hard thing to prove, right? I could do it by looking at a picture, but I'm trying to do this abstractly. That would be difficult. What's the definition of being connected? A graph is connected if that's a theorem. What's the definition of being connected? So I want to prove that no matter which 2 vertices I pick, there's a path, right? I'm not going to write this one down. It's a fairly short proof. Take 2 vertices, x and y. If the edge between them is in this graph, you're done. They're connected, right? So let's suppose that edge isn't in it. Then x and y are not adjacent, right? That means if you take all of the vertices that are adjacent to x and all the vertices that are adjacent to y, you have n minus 1 vertices. I'm excluding x and I'm excluding y. How many vertices are left in my graph? N minus 2. That means there's got to be at least 1 vertex. I counted when I touched it from x, and I counted when I touched it from y. I don't know what vertex that is, but there's a path of length 2, isn't there? That means that the diameter can never be bigger than 2. Gotta go back to my definitions. And that means if the smallest possible degree I have is n minus 1 over 2, then when I add two vertices together, I'll get n minus 1, and by that theorem, it'll be connected. By the way, this is a sharp bound. If you have even one vertex whose degree is smaller than n minus 1 over 2, you can't guarantee connectedness. There's actually an example in the text, well, written out a proof in the text on page 35. What if I had a graph that was disconnected? If you have k components and order n, we're going to go with order n again. What is pigeonhole principle going to tell me here? Discrete math told you couldn't forget this. What's the pigeonhole principle? Maybe you remember it by the other name, the Dirichlet drawer principle. Pigeonholes. That was the pigeonhole principle. You have the internet. Look it up.
There's n items and m containers with n greater than n. There has to be at least one container with more than one item.
N order k components. At least one component must have more than n over k items. That's the generalized pigeonhole principle. At the very worst, you have each one vertex being isolated from the rest of them, then you have n components, each of each of order 1 and size 0. I talked about multigraphs and pseudographs and loops and the way you count. What about digraphs? How is this different in a digraph? In a digraph, each edge goes out or in, right? Then instead of just having degree, you'll have out degree and in degree. And then each edge only counts once in the out degree and once in the in degree. So the total of the out degrees must be m, and the total of the in degrees must be m. We split it into two equal parts again, the handshake out and the handshake in. And since that's an asymmetric behavior, we're going to have to think about the way that works a little differently. More on that later. I hope you all have a wonderful rest of your day. I will see you all on Wednesday.